All right, great. So welcome all of you to the first session of our second day. And we have a session on counting by Dr. S. Muralidharan. He obtained his PhD in mathematics from TIFR. He has had the distinction of not only being at the helm of technology with his work in the private sector, but has also pursued his passion for academia. He has written more than 70 articles on mathematics in various journals. He has published 4 books, the latest one being Combinatorics for Mathematical Olympiads, which was released in January 2019. He was a chief examination coordinator for IOQM, which is conducted by MTAI. He was actively involved with the mathematics talent contest by AMTI for several years. At TCS, he worked on algorithms and data science and headed the Decision Sciences and Algorithms Lab and retired on 30th of October 2019. He has published 4 books, one on triangles, construction and inequalities, one on gems from a mathematics teacher, one titled Recursion Sequences, and Combinatorics for Mathematical Olympiads. Several of his solutions have appeared in the Canadian problem journal Crookes Mathematicarium. His article, The 15 Puzzle, A New Approach, appeared in the Journal of the Mathematics magazine, published by the Mathematical Association of America. His only hobby and passion is mathematics.
Thank you, Sai. Okay, my screen is visible to everybody?
Yes. Yes, sir.
Yeah. Okay, yeah. So we are going to do some basic counting today, and counting actually is pretty easy if you understand the basics behind any counting. And many students find counting hard mainly because they try to guess the answer, but guessing is slightly difficult, and there are mainly two main difficulties in counting. See, many counting problems start with in how many ways. So that is the usual counting problem, that is in how many ways some things can be done. For instance, in how many ways I can give change to 100 rupees with 1 rupee note, and then 2 rupee notes, 5 rupee notes, 10 rupee notes, 20 rupee notes, and then 50 rupee notes. So how many ways I can give change to this one? For instance, I can give it as 250 rupee notes, or 5 20 rupee notes, or 150 rupee notes, and then 5 10 rupee notes, and so on. So there are so many ways of doing this, but our aim is to count all of them, meaning how many ways are there to do this one. Okay, we'll do this problem if there is time. So every counting problem is starts like this: in how many ways can you do something? Okay. Uh, so there are exactly only 5 basic, let us say, let me call it as techniques, in which every counting problem can be mapped to. So you look at one of them, which is called the addition principle. See, the addition principle basically says this way. Suppose I have, let us say, 9 varieties of cakes and then 6 varieties of ice creams. I want to buy either a cake or an ice cream. So how many choices do we have? If I have to buy either a cake or an ice cream, how many choices do you have? Hmm. What happened? The whole class is silent.
Sir, 15.
15. Okay, there is 15. Why it is 15?
Sir, because the question says a cake or an ice cream.
Yeah, so I can take any one of those 9 cakes. Right? I can take a cake 1, cake 2, or cake 9. Or I can take any one of the, any one of the 9 cakes and any one of the ice creams, I1, I2, etc. up to I6. So this is, so since I have totally either this or that, so totally I have 15 choices. That means if I can do one thing, one task in, let us say, some m ways, and another independent task in n ways, and I can do one of them in m plus n ways. So that's what the basic addition principle is. So even though it looks a very, very simple principle, this is at the core of or the heart of many counting problems. Let us look at this. How many shortest paths are there from the point A to the point B along the grid lines? That is along the grid line. That means one of the path will be like this. I can just go like this. I can go like this. I can go this one path. The second path could be just this also. So note that every path, I am asking for the shortest path. That means every step should be either to the right or to the up. Because if I just look at this left step, then I am wasting one step because this left step has to be covered again by a right step. So this will be two steps. So that way, if it is the shortest path, I have only two choices. That is, at every point, I can have only either this way or this way. Again, at this point, let us say I don't have this choice. I have only one choice. Okay, I can go only this way. So if I do this, how many paths will be there between A and B? Between A and B. So let's see how we can attempt this problem. What are the possibilities? Of course, those who know some more math, and then they should keep quiet because for we want to give the option to the others. So to think about this problem. So suppose you are given like this, how will you approach this problem? Yes, Asma.
Sir, we know that each small path should be made of 6 rights and
Uh,
4 ups.
uh,
So, like the number of ways, like number of paths will be the number of ways to arrange these 6 rights and 4 ups,
okay.
and that will be like 10 factorial
Okay. You
divided.
know,
Yeah.
you know a lot more than okay. That is one way. Of course, I agree that this is a way of doing this one. I want to use only the addition principle, nothing else. Suppose I don't want to use anything else. What happens? I want to use only addition principle. Addition principle says if I can do one thing in m ways, another thing in m ways, I can do one or the other at m plus n ways. That's all it says, nothing else, right? Okay, so let's see how we can use the addition principle. Any other answers? Yes, Anant.
So like that's one way to get to the line which is to the bottom of the.
Okay.
Sir, can you show the figure?
Yeah, one second. I will come back to Madhusudan and then who else? I'll show you the figure. Yes. Yeah.
Sir, over here, like the line next to A, but
Hmm.
right to A,
Hmm.
it has one. We can go to the point which is right to A, one
Hmm.
in one way.
Hmm.
This the all the points in that line
Hmm.
can be reached only one way.
Yes.
Just like that, all the points above A
Hmm.
can be reached in one way,
Hmm.
and then the point which is diagonal to A can be reached in 2 ways.
Yeah. So now I have to reach this point means I can reach from here or from here. So this could be done in two ways. And again, this could be done in three ways, right? Because I can reach here two ways, here I can reach three, so it's three ways. This will be four ways, this will be five ways, this will be six ways, this will be seven ways. And this will be three, this will be, what will be that? I can reach this in three ways and can reach this in three ways. This point could be reached only from either this or this. So this I can reach in 6 ways. This will be
Sir, 10 ways.
10. This will be 15, this will be 21, this will be 28. And this will be again 4, this will be 5, this will be 10, this will be 20, and this will be, I made a mistake, so it is 5, 15, so it is 35, and this will be 56, and this will be 74, no, 84. and this is 15, this is 25, correct? And maybe I would have made a mistake, so let me check this way. Yeah. So here I have just written down how many ways I can reach any point from any point. For instance, this point could be reached from this point or this point, correct? So in that case, what will happen now? I have this is 10 ways and this is 10 ways, so this must be 20 ways. So I have 20 ways of reaching one point. So totally what I have here is that 210 ways of doing this, right? 210 ways of doing this one. Right. Now, let's look at this for instance. The shortest draw from A to B that lie below the main diagonal. So I don't want to cross this one. I can touch this one. For instance, one path could be, I can go like this, I can go like this, I can go like this, and I can go like this. Or another path is this way, like this one. So now how many ways I have, if this is the case? How many ways I can reach from A to B? Can I use the same way, same principle? Here it is 1.
Yeah, you can.
So 1, 1, 1, 1, 1. And this again is 1. This is 2. This is 3. This is 4. This is 5. This is 6. This is 2 again. This is 5. This is 9. This is 14. This is 20. This again is 5. This is 14, 28, 48. Like that. We can keep on doing that one. And if you do that, then I get this answer 132. Right? Now, 1 minute. You are 1 second. We have. Yeah. So can this be done in any other way? This problem? Who is this one? Who has raised a hand? No, I didn't see. No, no one has that. Yeah, can this be done in another way? Yes, of course. This one way is okay. This is fine, for instance, this way. And 1, 2, 3, 4, 5, 6. Okay, let me ask a different question. I have a movie theater. Okay. And there are 12 people standing in the queue. Standing in the queue. Now the cost of one ticket is 100 rupees. And everyone has either a 100 rupee note or a 200 rupee note. Now the cashier to begin with doesn't have change at all. So the cashier has no change at all. Cashier has no change. And there are exactly 1 by 1 minute. Let me give the correct problem, otherwise I'll be in trouble. So it is 1 by goes away, this goes away, and this is 2, this is 3, this is 4. Yeah, there are 12 people, and there are exactly 6 of them have 100 rupees, and then 6 of them have 200 rupees. So how many ways they can line up such that no one waits for change? No one waits for change. Let me repeat the question. I have a movie theater. There are 12 people standing in the queue. The ticket cost is 100 rupees. Everyone has either 100 rupees or 200 rupee note, and the cashier has no change to start with. So six have 200 rupee notes and six have 200 rupee notes. And so how many ways they can line up? So how many ways they can line up such that no one wants to wait for change. For instance, the first person cannot be a 200 rupee note, right? Because if it is a 200 rupee note, the cashier doesn't have any change at all. And then the ticket, of course, everyone wants only one ticket. So the ticket cost being 100 rupees, he doesn't have any 100 rupees change to this. So the line stops here. Correct? So the first one cannot be a 200 rupee note. Okay. So the first one can be 100 rupee note. The next one can be a 200 rupee note like this. So I can, suppose if I can arrange in such a way that no one has to wait for change. Suppose I have say this is my 100 rupee note is H, 200 rupee note is T. I have this is H, 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 T, 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 H, 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 T, T, T is one possibility. Because I would have got three H's and then three T's, then every 200 rupee note would have been given 1 rupee. Or it will be HT, HT, H, 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 and then T, 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 T. This is another change, another way of doing this one. So there are so many ways. Okay. So the question is how many ways? Question is how many ways? Looks like a hard problem, right? Doesn't seem to look like yes. Who is raising hand? Okay, there are. Okay, who raised hand? Yeah. Yes, Madhusudan.
Yes, sir.
Yeah.
But I just have one condition for this problem, sir.
Uh-huh.
The condition is that before you have a specific number of 200 rupee notes, for example, if you are putting for 200 rupees notes, that definitely has to be 400 rupees notes before it.
No. Say that again. Before I put a 200 rupee note, that should be
So
200 rupee note.
yes, sir. For example, you put 200 rupee note. Then before that definitely has to be minimum 400 rupee notes.
That is correct. That's correct. Yes.
So, sir, there are 12 ways, sir.
There are 12 ways. How?
The first way is as it's given HT, 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 HT.
No. That's only a specific case. For instance, if I have the first one has to be H, that's for sure. The next one need not be T.
Oh, yes,
Next
sir.
one also can be H.
Yes, sir.
Correct?
Yes, sir.
Mm.
So
That's
that
my-
means
mm.
so that means the answer is 11 factorial.
11 factorial. Why 11 factorial?
Because there are 11 different ways it can be arranged.
For instance, if I have H is the first one, if I have two T's here, then we are stuck, right?
Oh, yeah. Oh, yes. Yes, sir. That means 7 factorial. Sir, I'll just give me some time, sir.
Sure. Okay. Yes, Asma. You raise your hand? Yeah, yes, Asma.
That at any instant, the number of 1,000 rupee notes should not exceed the number of 100 rupee notes.
Yeah, number of 200 rupee notes should not exceed. Yeah, that's correct.
Sorry. Not
Yes.
okay.
Yes.
Yeah, so it's actually very similar to the previous problem.
Excellent.
In the previous problem, the number of ups should not exceed the number of rights.
Exactly. Brilliant, Asma. Really brilliant.
Thank
See,
you.
this problem can be mapped to the one which we just now did. See, look at this figure. So if I really look at this one, so the number of, so suppose for every 100 rupee note, I draw a horizontal step, and for every 200 rupee note, I draw a vertical step. So if I just draw this, first one is S, the second one is T. 2 has to be this one. So if I do that, so the number of vertical lines below this one, the number of at any point in time, for instance, here, what's the number of vertical lines up to that point? Only 3. What's the number of horizontal lines? 5. So if I just look at all these things, if I look at this number of ways of reaching this one, 132, this B, there are 6 steps here and 6 steps here. So every step, every horizontal step will be the number of horizontal steps at any point. Take any point here. Because what is this line? This line is, this is the line where the number of horizontal steps is equal to the number of vertical steps. So below that, number of vertical steps will be less than the number of horizontal steps. And that's really what we want. That's really what we want. So this problem is the same as the cashier problem is the same as this problem in disguise. So Asma did a great job. This is the number of ways of arranging 6 100 rupee notes and then 6 200 rupee notes is basically 132. Is 132. So now here it is. In fact, if I have instead of 12 people, suppose I have 2n people, where n have 100 rupee notes and then n have 200 rupee notes, then of course I can't find n using this one. There are some more text. This is actually what is called a Catalan number. This has very rich history, and in fact I can give you some of the other things. So let us look at let us look at, suppose I multiply say 12 numbers. I'm going to multiply 12 numbers, and how many ways we can introduce brackets so that it makes sense. For instance, suppose I can do A1, A2 and then A3 like this, because see, addition means what? Okay, addition or multiplication means what? When we multiply, we take 2 numbers and multiply, correct? 2 numbers and multiply. So how many ways I can introduce these things? That is the number of ways and so on. Suppose if I have 4 of them, A1, A2, A3, I can do it this way once.
Hello,
Or,
Murli sir.
yeah.
Sorry to interrupt. Can
Mhm.
you turn on your camera so we can spotlight you?
See, I'm using an iPad, so I'm keeping it down and then I won't be visible.
Okay, so for
Let
taking
me
some
check. Let me check. Okay, let
okay,
me.
for taking
Because
some screenshots, it
if
is
I
better if we can spotlight you.
1 second. If I keep that, let me see. I can. Am I
Okay,
visible?
yeah, you're
Yeah.
visible. Thank you, sir.
Yeah. Because I can't keep it in this. What is that? In this position and then right also, right? That's the problem I have. Okay. Right. Anyway, let's go ahead. Oops. Let me switch off the. Okay, not a problem. 1 second. Yeah, so what we have is that, so here I have 2 ways of doing this one. So this also boils down to Catalan numbers. This also boils down to Catalan numbers, right? That's what, let me switch off the camera so that I can start writing neatly. Right. Okay, let's look at, so this is a nice problem, and then, okay, we'll come back to this problem. Let's look at this one. Consider the walks in this one between 0, 0 and 6, 6. It's similar to that. Only thing is, what we have is that this is going through this 1, 1, 3, 3, 5, 5 is forbidden. So how many ways I can reach 6, 6 from 0, 0? Of course, the shortest way, again, we already said that it's always 1 east and 1 north. Always. Okay. So the same way I can do, this is 1, 1, 1, 1, 1, 1, 1. This again is 1, 1, 1, 1, 1, 1, 1. Then can you do this now? Can you check what happens here?
I mean, like 1, 1, that coordinate we are not supposed to pass.
Yes, I can't see. For instance, this is a red one. Let us say, I can't go through this like this. So when I am below this red, and then this path is forbidden, because if I just go there, then I will get stuck there. So let us say these are all let us say ponds. So if you go there and then you will get sunk in the pond. So I can't do this. I have to avoid those ponds. So if it is there, then what will happen to this? For instance, here also I can't come from here, so I can go like this only. I can go like this only. So here I can go like this. So this will be only 2. Of course, this can be 2, this can be 3, this can be 4, this can be 5. This can be 4, this can be 7, this can be 11, this can be 16. But this will be 1 and 1, this is 2, this is 4. Because from here to here I can come, but here I can go and here I can go. That's all. So check what happens. How many ways I can reach this? Hmm? How many ways? Susan, you wanted to say something?
Yes, sir. Sir, I found a method to find the answer for the previous sums, sir.
What is that?
Sir, as the previous sum we saw, the diagonal sum, this one. I figured out that it is basically the number of units you can move to the. I'm taking the number of units you can move to the right as n, and the number of units you can move to the up as m.
Okay.
So if it's a square and the diagonal is like this, the answer is n into n plus 1.
So it is n into n plus 1.
Yes.
Here I have only 6 here.
Yes.
So n is 6. So it is 6 into 7, only 42.
Oh no, it's 11 into 12. Sir,
How is it 11?
1 second, sir. I'll be back, sir. 1 minute. Sir, I got it, sir.
You got it?
Yes, sir. But this method only applies for a square.
That's okay. So this is a square, okay. But I want the ones which are below the diagonal.
Yes, sir. For the below the diagonal, the answer is 2n into 2n minus 1.
2n into 2n minus 1.
Yes.
Okay. Let us check whether it works. 2n into 2n minus 1. This should work for any n?
Yes, sir.
Okay, let us check whether this works for this n. How many n's I have here?
1, 2, 3.
This is 4.
4.
1, 2, 3, 4. So if it is where n is 4 or 2n is 4?
N is 4, sir.
So this will be 8 into 7.
Yes, sir.
56, but I have only 14.
Okay. I think I messed up, sir. Sorry.
Yeah. See, okay, this is a good, okay, it's a good mistake to make. Most of the time, what we do is that in counting problems, we think something works. Okay, there is one small principle which you have to follow, which if you follow, it will be useful for you. So whenever you guess an answer, something like this, whenever you suppose you guess, for instance, you guess the answer as 2n into 2n minus 1. Check whether this is true for small n, where you can hand calculate. Suppose you see whether it's true for 3 or 4 or something. Here we saw that it doesn't work for 4.
Okay.
Correct? So that's a very, very good thing to this, what is usually called a sanity check.
Okay, sir.
So whenever you guess an answer for any counting problem, do a sanity check. Particularly if it involves n and so on, do whether the same thing will work for small values of n.
Okay,
Okay,
sir.
right. So let's see whether we got any answer for the other one. This one.
Sir, I'm getting 132, but I'm not sure whether it's right.
Yeah, 132 is what you will get, definitely. Here also it's the same thing. So here I have 2n and 2n. And this also will be the Catalan number. See, the Catalan number occurs in more than about 200 some occasions. In fact, there is a book by title Catalan numbers. That book contains around 217 instances where the answer is Catalan number, nth Catalan number. Okay. Anyway, that's because this is very this you will meet in higher mathematics in several places. And anyway, that's the this again another problem in this one. This is a very easy one, so let us skip this and then let us go to something interesting. Yes. So note that we have not used anything other than addition principle. Okay. Now Iris is playing a game. It's like a board like this one. The goal is to get the game piece from this place to this place. And she can move the game by any number of moves. For instance, it could be like this, or she could move like this, or she could move like this, or she could move like this and then like this and so on. So she could move horizontally or vertically by any number of squares. So previously in the problems, we can just move only by one square or one step like this. Here I can move like this. Okay. Now the question is, how many ways there can be this iris can make this this piece to this piece from that spot. So for instance, this move is considered different than this sequence of these moves. Okay, so this whole move is not the same as this move. So the number of moves is what I have to count. Correct? What I have to count. Now, how many ways I can move this star to the next move? I can do it only one way. Correct? How many ways I can move it to this square? Second square? How many?
I think 2 ways. Because you can jump into the square behind it and then go to it, or dash.
Exactly. I can move it in 2 ways. This will be 2. What about this?
3 ways.
3 ways?
Like you can jump, like since the star can move one by one. So as you say, so if it
Is
moves
it
from one,
3? Is it 3 or
Sir, 4.
4? Why 4?
Sir, you can like go one step at a time,
Hmm.
and or you can go for all 3 steps, or you can go the first step and then 2 steps, or go 2 steps then 1 step.
So I can just like one by one like this. Then, or I can go like this.
Yes, or you can go directly,
Uh,
or you can go to
Sir,
the first
eh?
one, or you can go
sir,
directly to the
sir,
next
the
one.
first one and then the next 2 steps
This one and
directly.
the next 2.
Yeah.
Okay, so this will be 4.
4 ways.
What about this?
Sir, 8 ways.
Why 8?
Sir, first you can move one by one. Then you can move all of the 4 steps at the same time. Then you can move 3 step, yeah, 1, 2, 3 steps, then 1 step. Then you can do 1 step and 3 steps. Then you can do 2 steps and 2 steps.
So I have to change, I have to, meaning sort of brute force, sort of, what should I say? List down all of them, is it? What
No,
you are
sir.
doing is that you are listing them down.
Yes, sir.
Is there any other way? See, note that I am using only addition principle.
Sir, I think there is another way, sir.
What is that?
Sir, like first you calculate the number of steps from the first step. You can go 4 ways. And if you make directly 2 steps, there are like 2 more ways. And then if we go directly to the third step first, then there is 1 way. And there is also, you can also move directly to the 4th step.
So if
there
so if I just put this 1 here, at every stage it is it's the sum of all the numbers to its left, right?
Yes.
Here it is 1, here it is 1 and 1 plus 1, here it is 1 plus 2 plus 1 plus 1, here it is 4 plus 2 plus 1 plus 1. Correct? So that means every step it will be just the previous. So it is a sum of all numbers to the left.
Yes. Or I
So this
can
again, it is 2, this is 4. Sorry, I'm sorry. This is this is 1, this is 2, this is 4, this is 8. What about this? This point.
Sir, there are 2 ways.
There are two ways.
There are 2 ways.
What about this one?
4 ways.
4 ways.
Think again.
3 ways.
Hmm?
3 ways.
How many? 3 ways.
3.
Why 3?
Well, I thought like as it can move as the number of ways, so 1 step ahead, and it can also like move to the right side. So like
No, I can reach this. I can reach this one in 2 ways and this one in 2 ways. Definitely, I can reach it in 4 ways, right?
sir, I didn't get.
No, I can reach this square in 2 ways, and I can get this square in 2 ways. So this square can be got from either from this square or from this square. So this is 2 and this is 2. By addition principle, this will be at least 4 ways, if not more.
So there are more, sir. There are
More.
ways.
What are they? Or how many more?
Sir, but I haven't counted it properly. Sir, like if we go from the 2 in the first row, third column thing, the 2, then there's only 1 up left, so that is 1 move. That is 1, 2 times, so 2 ways. And then from the other 2 to go right, there's another 2 ways. And then from the 1 after the when we go right there, we land on a 1. That from there are 2 ways. And from when we go up there is 1. There is 1. And if we go that one also, there's 2 ways.
So
8 ways.
8 ways. Oh. 8 ways. Okay, what did we derive when we looked at this as 4? What did we say?
It was like the sum of all the previous.
Left of them, correct? So why not? Is it not the same thing true here? Here also? Here also? So now what's the only difference is that it is sum of all the numbers to the left and all the numbers below as well.
Sir,
Because I can come here.
Sir, that can be contradicted, sir.
Why?
Sir, because if we add all the numbers to the left and bottom of it, the sum will only be 7.
It will be 5. It will be 5.
Which will be, sir?
At this point, this is only 5, right? It's not 8.
Yes, sir.
Did you count 8?
No, sir. I only counted 7.
7. Where is the other 2?
Sir, the
Okay, so
one
how many? 1 second. So if I
Sir, I
reach
think I
here
made a
in one
mistake.
way, if I reach here in one way, how many ways I can reach this place? How many ways I can reach that place?
Sir, which
I
place
reach.
are
Huh?
you talking? Which
Hmm?
place are you talking about?
No. If I reach this spot,
Okay.
how many ways from this spot I can reach this spot?
The two
Sir,
ways.
2 ways.
2 ways. So that is 2, correct? Obviously. If I reach this spot, how many ways I can reach that spot?
The one way.
1 way.
1 way. I added that. If I reach this spot, how many ways I can reach the other spot? If I reach this spot, how many ways I can reach this spot from here?
1
The
way.
one way.
Huh?
one
One.
one
1 way, right? But I can reach this spot itself in 2 ways, so it will be reached in 2 ways. So totally 2 plus 2 plus 1. So this spot, sorry. So this one is, this is 1, this is 2, this will be 5. This also is 2. And this is 4 and this is 8. Now if I want the number of ways of reaching this guy, what I should do? I
Add
should
4,
add
5,
all the
yeah.
numbers to the left and all the numbers down. So how many ways I can reach this spot?
12.
12 ways. What will be this one? It will be
28.
28 ways. So you can just keep on doing this one. So the only thing to understand here is that, so whenever I want to reach any one thing, I could have reached this one and directly, or I could have reached like this, or I could have reached like this, or I could have reached like this, and so on. So everything will be to the left as well as the down below also. So whatever number of ways of reaching each square, I have to add to that one because I reach that square and then one jump will get me to the required square. So the rule is this. The rule is that whenever I get any square, if I want to get to this square, so I can reach from this square or this square or this square, or I can reach from this square or this square or this square. So if I add the number of ways of reaching all these things, and then I can get one, and then if I add the number of ways of reaching all these things, I get the other. So this will be the number of ways of doing this. Correct? Right. Now let me ask a question. Instead of, I said that instead of no, okay, we will, okay, so let's complete this problem so that it's easier now. So here I have, for instance, I have written the answer here. So the thing is, for instance, this 37 is sum of these 3 and then those 2. So what is this 12 now? The 12 will be the sum of this one and then these 3. So if I just add all these things up, in fact, there are as many as 838 ways of moving the game piece from here to here. Right? And note that it is a simple addition principle, nothing else. Simple addition principle. So this addition principle is strong enough to solve this problem. So let me check one more. No, not this one. Let me check. Okay, let me. Either this problem or that. Okay, let us look at this frog jump problem. Yeah. So a frog we have positioned in here in 0, 0. And any time it can go to the next one horizontally or 2 steps horizontally or 1 step vertically or 2 steps vertically. Correct? So I want to count the number of distinct steps which can reach 4, 4. For instance, it can 2 here and then 2 here and then 1 and 1 here and then 2 here. This one sequence of steps. So that way, how many such sequence of steps are there? How many such sequence of steps are there? So can we find a simple rule for doing this? Just as in the previous problem, we said that it is all it is basically it is the all the numbers to the left and all the numbers down below.
So the same rule can be applied here.
Same rule, all the numbers to the left.
Yes, sir.
I see. See, but this one, if you look at this one, I can reach only from here or from here.
Yes.
I can't reach directly here. Correct?
Yes.
So should I add this number or only these two numbers?
You're only required to add these two numbers over here.
Exactly. So whenever I am at any point, I have to add two numbers to the immediate left and two numbers immediate below. The two immediate left numbers, and then two immediate down numbers. So if I do that, then I will get what's the, for instance, if I have like this. So I have 1, 1, these are, so this one is immediate 2 is 1 and 1. Here immediate 2 is 1 and 2. Immediate 5 is 2 and 3. So I have added that way. And similarly for this one. So here, for instance, in this 84, how do you get 84? The sum of these two and the sum of these two. Sum of these two and the sum of these two. Okay. So the rule here is that just as the rules of jumping is that it can jump only one step or two steps. Suppose if I say it can jump one step or two step like this, and also one step or two step diagonally like this also, then what should I do? How will the problem change?
You should also include the diagonal point.
Yeah.
Exactly. So in this case, what will happen is I have to include a diagonal point also. So here it will be 1 and 1. This will be 3. This will be 3. This will be 3. And then here it will be, this is 2. This will be again 3. And this is fine. So this is 2 and 3. And then this will be 6. Because it can diagonally also jump. So depending on how the jump happens,
Sir,
so we
isn't
can...
it 7, sir?
7...
But because there's a 1 before the 3.
There is a...
1
No.
before that.
This
Isn't
one.
it 7?
This one.
Yes. Yes, sir.
This is here, okay.
So the 2
I
would
can
have.
come from here only, right?
So we can also go up or right.
Yeah.
And the one below it is 2. And you told the one to the left of the 5 thing is 3, sir, you told. And before that, this is a 1, sir. So 1 plus 3 plus 2 plus 1 is 7, sir, not 6.
Where? Here.
To that 5 point only.
It will be 5 only, right here.
That should be 7, sir.
That should be 7. Why? If I allow the diagonal jump, is it?
Yes, sir.
If I allow the diagonal jump, there's only one diagonal jump, isn't it?
But the two steps from left to
No.
right.
2 steps from
Left.
No. Where is the 7th one?
No, sir. Like the question was, you can go 1 step or 2 steps left to right, 1 step or 2 steps down to up. You can also go 1 step or 2 step diagonally, sir.
Diagonally means from here, the
Yes,
2
sir.
step diagonally is this way.
Yes, sir, I know, sir.
Ah,
So shouldn't
that-
it be, sir, you
No,
told
this is not 2 step. No, this is not 2 step diagonally. If you are meaning this way, is it?
No, sir, no, sir.
Ah.
I'm telling, since the point to the left of it is 3, sir. The number
Left
of
of it is 3. Yeah, that's correct. Oh, yeah, I understand. Yeah, okay. So this is 3. So okay, so that is 3. Oops, what I'm saying. This is 3. So this is 2 only.
Yes, sir, that's 2.
So this is 3 plus 2, 5, and then this one more thing will be 6, isn't it?
Sir, but what about the point to the left of 3? You can go 2 steps to the right now, sir.
No, that I have already taken care of, right? This is 1 plus 2. This is 1 plus 2 plus 2 plus 1.
Oh.
No, sir, that's a diagonal at the first square, like the square which contains the origin one.
Oh, okay. So this is right. So it is 3 here. So that means it is 4 plus this is 6 again. Ah, yeah, you are right. It's 7. Yeah, you are right. Yeah, 7. Yes. Yeah, you're right. Correct. Yeah, it's 7. So anyway, so the rule is that. So if I am adding diagonally, then definitely it will be 7 now. Correct? Yes. Nice. Okay. Now let us look at this problem. How many 9-digit numbers are there formed with digits 1, 2, and 4, in which 2 and 4 do not occur next to each other? That is, I want to find the 9-digit numbers. Okay. And then in which 2 and 4 do not occur next to each other. This is one example. Okay. Note that it is not necessary to use all the 1 and 4, all the 3 digits. It could be just 1, 1, 1, 1, 1, 1, 1. That is fine. It could be just 2, 2, 2, 2, 2, 2, 2. It could be 4, 4, 4, 4, 4, 4, 4, like this. And then say 1, 1, 1, like that. That also is possible. So how many such numbers are there? I want a 9-digit numbers. This 9-digit looks like a bit long. So let us say how many 3-digit numbers will be there? Or how many 1-digit numbers are there?
The number of one-digit numbers will be 3.
3. How many 2-digit numbers are there?
So 7.
87.
Huh?
7, sir.
Which is 87? Which is 87?
2-digit numbers. There are 87 2-digit numbers.
87.
Yes.
I want to use only
Sir,
1,
7,
2,
sir.
and 4.
Yes,
Sir,
sir.
7.
Sir, only 7.
Sir, there are only 7, sir.
7, sir.
1, 2, and 4. Only those
Yes,
3
sir,
digits are
7.
used. How can that be 87?
Oh, sorry, sir.
Yeah, at best, it will be only 9, right? Maximum is 9 anyway, because I have to fill 3 slots. So, okay, maximum is 8 only. So 7 numbers are there. 2-digit. 3-digit numbers.
Sir, if there are 8 first, then it should be 6, sir.
Hmm?
Sir, if total number of 2-digit numbers are 8, then wait. Sir, isn't the total number of 2-digit numbers? Yes.
Is it 8 or something else? Yeah.
There should be 9, sir.
9.
So the number of 2-digit numbers forms are 9, but with that rule it's 7 only.
9. Okay. So the number of 2-digit numbers using 1, 2, and 4, because the digits can be repeated. So this will be 9. So out of that, only 7 are what? Do not
Sir,
have
7 are do not adjacent.
2 and 4 not occurring adjacent to each other. So how do we use the addition principle to get this one? So let's build a table like this. Huh? Pardon me? I didn't hear that. Okay. Let's see. So this is the, what I'm going to do is that I am going to fill this table. What is this table? So this slot will contain the number of 5-digit numbers that end at 2, that end at this one. So this will be number of 7-digit numbers that end at 1 will be filled up here. So now let us look at how to fill this table. So now the number of 1-digit number ending at 1, how many are there?
Only 1.
1. Number of 1-digit number ending at 2?
Only 1.
1.
1.
Now how many numbers are there? 2-digit numbers which end at 1?
9. 9.
3.
And 2-digit numbers end at 1 and then using only the digits 1, 2, and 4.
3.
3.
3, sir.
3. How many numbers are there which end at 2?
3.
3.
Sir, 2. Sir, with the rule 2.
How it is 2? See, the first, no?
No, sir. If the first digit is
This
a
number
4,
is last digit is 2.
sir,
So I
first
have to
digit
have
cannot be 4.
uh,
First digit cannot be 4.
so
Oh, yes, sir, with the rules.
2
mm, it
But
could
it
be
is two number.
That's why
the first digit cannot be 4. So it could be
1 or 2.
1 or 2. There are only two numbers here. And this one?
Same 2.
2.
Also 2.
Two.
What about this?
The 9.
How
Plus
9?
7, I think.
See, the number ends at 1. That is, I want the number ends at 1. Correct? So this is a 3-digit number. So what are these numbers now? What I can say about this one? The number of 2-digit
So there are
numbers
2
here.
digit numbers.
And that can end at either 1, 2 or 4, right?
So that's 7.
Suppose the third digit is this one. So I have 2-digit numbers. I want all the 2-digit numbers which end at it could be ending at 1 or it could be
Sir,
ending
it's
at
the
2.
sum of the three,
Sum up,
the three
I can
in the
add these
in the
3 and 7.
7.
Here,
uh,
the last digit is 2. The previous 2 digits, this cannot be 4.
sir 1 plus
So
2.
3.
I can add only these two numbers here.
The 1 1.
Which is
It
5.
could be, this will be
5.
5. For this one,
For this one, 2 shouldn't
5.
be coming
I
next
can
to
add these
5.
two
5.
numbers. That will be 5 again. So the rule is now very clear.
Then we can fill the rest of the tab.
Yes, this 1, 1, 1, this is 3, this is 2 and so on. So for this one, what will be this? This is
17.
17. This one will be
12.
12. This will be 12. This will be 24. So 41. This will be 29. This will be 29. So we can keep on doing this one. Correct? So if I just fill this one, what I will get is this. So every time, so this 577 is the sum of this one, this one, this one. This 408 is the sum of this one and this one. Correct? No, wrong.
So the top 2 ones.
Top and
The next one.
this
Below
one.
it.
Yes. So this 408. This 408 is the sum of this one
Yeah.
and
the bottommost one.
bottommost one. And now I know how many are there. So if I just keep on doing this, then 1393, if 995, 995. The total thing is 1393 plus 985 plus 985. Whatever that number is, I don't care. So this is the total number of 9-digit numbers which end at either 1, which use only 1, 2 or 4. Where 2 and 4 do not occur next to each other. So 2 and 4 or 4 and 2 also cannot occur, right? That's what we have already factored it out, right? Okay, right. Now let's see. Total number is, of course, 3363. Let's look at one nice problem. We have how many ways I can give change to 100 rupees in 1 rupee, 5 rupee, 10 rupee, 20 rupee, 50 rupee notes. Okay, how many ways I can change? So suppose if I have, let us say, A number of 1 rupee notes, B number of 5 rupee notes, C number of 10 rupee notes, D number of 20 rupee notes, and E number of 50 rupee notes, then I must have A plus 5B plus 10C plus 20D plus 50E must be equal to 100. Correct? That's what I have to
Yes.
do.
Then E
So,
is greater than, less than or equal to 2.
yeah.
E is less than or
E is
equal
less than or equal to 2. E could be 0, E could be 1, E could be 2. If E is 0, then I need how many ways I can do if I by B plus 10C plus 20D is equal to 100. If E is 1, I want A plus 5B plus 10C plus 20D is equal to 50. If E is 2,
Then all of them are 0.
yeah, only one way, that is 250 rupee notes, and we are done anyway. So that's one way anyway. So then I have to find out how many ways are there for this and add it to this one. Correct? Now,
Yes.
okay, so let us again, just as in the previous problem, I'm going to make this table. Right. Now, can you guess why I am listing only 5, 10, 15 up to 50? Why not 6? Why not 8?
So because
Numbers
the
become divisible by 5.
Hmm. These are divisible by 5. But am I looking at all the cases in which 1 rupee notes are also used? Suppose I am giving change to, let us say, 100. I have already given 75 rupees in 5 rupees, 10 rupees, 20 rupees, 50 rupees. Then I want, let us say, I want to give a change to, let's say, 78, let us say. Then I have to, there's only one way of doing it after, because 3 1 rupee notes is the only thing I can add. Correct?
Yes.
So, yeah. So if I just do this 1 rupee notes, I can always ignore. That means if I just delete the 1 rupee notes, in the change, the remaining will be, I can
Multiples of
always,
5.
will be
They will be like multiples of 5.
multiples of 5. That's correct. So if I look at all these multiples of 5 and then add that, meaning to, for the remaining thing, I can just add 1 rupee note, then there is no issue at all. That's already counted here. So I'm going to count this way. Okay. Suppose I use one 5 rupee note. That is, okay, I'm going to give, let us say, I'm going to give change for 5 rupees. How many ways I can do that? I can give 5 1 rupee notes or 1 5 rupee note, correct? That's the only way. No other way. So if I use only a 5 rupee note, that's only one way of doing that. If I use 1 rupee notes only, no 5 rupee notes. If I use 1 rupee notes only and 5 rupee notes, then it will be how many ways I can give? Again, I can have only one way. That is either it is 1 1 1 1 1 or 1 5 rupee. So how this table is built is like this. So this is in this column. So what I'm doing is that I have how many ways I can give change if 5 rupee notes is used. For instance, let us select 2. So if 5 rupee notes is used to give change for 10, how many ways I can do? If 5 rupee notes is used for making change for 10 rupees.
2.
Why? Because I can use 5 plus 5 or 5 plus 1 plus 1 plus 1. Note that 5 rupee notes have to be used. So the remaining thing is 10. And if for, let us say in this case, here, if I use 10 rupee notes, at least one 10 rupee note, and I want to give change for 20 rupees, how many ways I can give? So one 10 rupees already given. So what are the remaining things? What's the remaining amount to be changed? 10 rupees. How many ways I can give change for 10 rupees? Where can I get that one?
4 ways.
Huh? I can get it in this way. So if one 10 rupee note has to be changed for 20 rupees, and I already have 10 rupee notes given, the remaining 10 rupees can be, that change could be found by adding all these 3 numbers. Okay, that's why we get 4 here. Now let's look at this, for instance, 9. How do I get 9 here? What does it mean? I am giving change for 30 rupees. One 10 rupees already given. So what's the remaining number? 20 rupees. How many ways I can give change for 20 rupees? Where can I get? I can get it from here. Note that I can't add this guy because that will use 20 rupee notes. Because if I use only 10 rupee notes, maximum is 10 rupee notes, I can give 9. Suppose I want this 10, how will I get that? That means I have used a 20 rupee note for giving change to 40 rupees. The remaining has to be 20 rupees. How many ways I can give change to 20 rupees using 1 rupee, 5 rupee, 10 rupee, 20 rupees? It will be these 4.
Yes.
So what's the rule here? The rule here is that if I want to fill up any row or any column, if I want to fill up this row or this column, 20 rupees is used. What's the number? What's the total change? 35. So the remaining is 15. The remaining 15, how many ways I can do? This will be this will be 20 rupees. So this will be, what is that again? 35. Yeah. So 60. This what I'm saying. The
Okay.
remaining is 15 rupees. So these three things. 136. If I keep on filling that, then I get all about this. So totally, the number of ways of changing 100 rupees is that the sum of these four things. Okay. So here also note that we use just addition principle, nothing else. We used addition principle, nothing else. But only thing is that we want to first of all understand the problem in this perspective and then build this table. So that's where this becomes slightly a bit, I shouldn't say complicated, but meaning, what should I say? It becomes a bit innovative. Okay, I won't say it is complicated, it's innovative, right? Okay, so let's see what we have done today. Let's see. We have anyone has any questions? No questions. That's a bit odd. Does it mean that everyone has understood everything? Let me show my face. Okay. Right. So now, if you have already understood this one, so let us, since we are meeting tomorrow as well, so let us look at one more principle called the multiplication principle. Multiplication principle. This again is easy. The same way, suppose I have I have 9 cakes and then 6 ice creams. I have 9 cakes and 6 ice creams. And your father is generous, so he says that you can take an ice cream and a cake. You can take an ice cream and a cake. A cake and an ice cream. So how many choices do you have?
54.
54, because I can choose the cake 1, ice cream 1, cake 2, ice cream 2, and so on. So I can say cake 9, then ice cream 6. So there are 54 choices. This is the basic multiplication principle. Oops, what I'm saying. Oh. Oh no. Let me. Oops. Yeah, sorry. Oh, no. Okay. Oops. Doesn't work. Yeah. No. 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 Yeah. So if I have, sorry, I can take this one. So now we want to use this. This is actually at the core of several important ones. Suppose I have, let us say, I have 6 people, 6 students. I want to make them stand in a row. All the 6. How many ways I can do that?
6 factorial.
Yeah. So the first one, suppose the students are say S1, S2, S3, S4, S5, S6. How many choices this has?
This has
6 choices. And after standing one person, I have 5 choices for this, 4 choices for this, 3 choices for this, 2 choices for this, 1 choice for this. So now it is hand, isn't it?
Sir, just a gentle reminder, we are left with the 5 minutes.
Yeah, I'm going to close.
Okay.
And. So whenever I see an and in a combinatorics problem, in a counting problem, we can multiply. Okay. So how many ways I can send them? It will be 6 into 5 into 4 into 3 into 2 into 1. So this will be, it will be
720.
factorial.
So 720.
Yeah, it is 6 factorial. It's usually written as 6 factorial, right? Okay. Now the next problem is that suppose I have 6 students. I want to choose 3 of them. I want to choose 3 of them. So how many ways I can choose 3 from 6?
Sir,
Now,
6 into 5 into 4.
oh, I see. Very good answer. I was waiting for this answer. It is 6 into 5 into 4. So suppose, let us do a sanity check for this. Suppose I have 4 students. I want to choose 2 of them. According to your thing, it is 4 into 3, right? Isn't it?
Yes, sir.
Okay. Suppose the students are, let us say, A, B, C, D. So it will be, I can choose A and B, I can choose A and C, I can choose A and D, I can choose B and A, I can choose B and C, I can choose B and D, I can choose C and A, I can choose C and B, I can choose C and D. When I say choose, order doesn't matter, right? Therefore, this one and this one are the same. As a team, they are the same, right? Either A, B or B, A. And this one and then this one are the same. So how many such choices will be there? How many things will be the same? Here, everything will occur twice, right? So that means it's not 4 into 3, it is 4 into 3 by 2.
Oh, yes, sir. I'm
So,
sorry,
yeah,
sir.
yeah, we will see, we will stop here because this is going to be an important and interesting concept which we will explore in the next class. And this is at the core, of course, there are, whenever somebody mentions the name combinatorics, they always say that it is permutations and combinations. Permutations and combinations. This is basically arranging, which we did here. This is basically choosing. There's only a minor difference between these two, and we will explore that tomorrow, and then we will meet again. Thank you very much, and it was interesting teaching you, and we will meet again tomorrow. Any questions finally? Oh, okay, good evening. Bye-bye.
No, sir.
Huh? Yeah, pardon me?
Thank you, sir. Good evening.
Oh, thank you. Bye-bye. Bye. Yeah.
Thank you, sir.
Thank
Yeah,
you,
I was
sir.
very happy with Asma, who found the brilliant connection between the Catalan numbers and then the cashier problem. Okay, good. Thank you. Bye-bye.
Thank you, sir.
Bye.
Thank you, sir.